Hopefully this is or should be review from Monday's lecture. So we talked a little bit about Lewis symbols. The symbols are for ions, how many electrons are around and can be given or taken. This is a way to keep track of electrons. And we write it in the chemical symbols with dots for representing each electrons. We also talked about group numbers, which you should remember from chapter 1 or chapter 2. And we notice this nice trend of the valence electrons, the electrons that will interact with through bonding. The number of electrons is equal to the number of group. So group 1A has 1 electron, group 2 has 2 electrons, and so forth. We see the same thing for 5A through 5A through 8A. Again, with the exception being helium. So if you remember from chapter 6, we talked about the group, or the shell, I should say. So the shell equals 1. When n equals 1, it can only hold 2 electrons. When n equals 2, you have the s orbital and the p orbital, which can hold 8 electrons, and so forth. But you can see that there are 8 electrons around the noble gas configurations. We also talked about, or hopefully we talked about, how electrons are transferred through ionic bonds. So remember, in ionic bonds, electrons are taken, not shared. So the sodium, which is in group 1, has 1 electron it can give up. Chlorine has a vacancy of 1, so the electron from sodium wants to go to the chlorine, fulfilling the octet rule for chlorine, and then also having that nice clean sodium where there's not any lone electrons. Same thing with magnesium. It has 2 valence electrons. Oxygen has 2 holes or vacancies. So those electrons can go and fill the holes of oxygen, resulting in a positive 2 magnesium and a negative 2 oxygen. And notice how there's 8 electrons around oxygen, 8 electrons around chlorine, and no electrons around the cation. This obeys the octet rule, again, where atoms tend to gain, lose, or share electrons until they are surrounded by 8 electrons. Now again, there are exceptions, but we've talked about this before when we were getting into periodic table trends and things like that. Remember how energetically atoms want to either have a full electron configuration or half. So fully filled or half filled is more energetically stable. We now have a name for that rule, and that's called the octet rule. So we can see that these have the noble gas configurations. So if we look at polyatomic ions are covalently bonded elements that have a charge. So they are important for ionic compounds and ionic bonding, but there's also covalent bonding going on between the 2 nonmetals inside the ion. So you can see that we have nitrogen and hydrogen. Both of those are nonmetals. 2 nonmetals means there are covalent bonds that are occurring. As a reminder, this again should be review at this point. Covalent bonds happen between 2 nonmetals, and atoms share electrons. So we have to think about it differently than the ionic compounds, where ionics, you can see the electron in the Lewis symbols, it gets removed, and you have 2 charged species. Here, we have to think about attractions and repulsions, because now we don't have 2 individual ions, we have 2 atoms that have the orbitals overlapping, forming a region where electrons can transfer between one atom to the other. So when we talk about shared electrons and bonds, what this means is there is an attraction between the electrons and the nuclei of the two species. But you also have to think about the repulsion. So the nuclei is positive, so two positives repulse. Two electrons, they're negative, so they also repel each other. So you have uh, some species that are positively charged. So if the nuclei are too close together, the positive charges start to repel. If the electrons are too close together, they start to repel. But there's also an attraction between the electrons from one species to the nuclei to the other. So all these interactions must be considered in a bond. For my visual learners, what we can see is, if you recall from chapter 6, we don't know where the electrons are exactly, but we do have a probability density that we call the orbital. When two atoms get closer and closer together, the positively charged center, so you see here, let me get my pen. You can see here, circled in red, the positively centered of this atom and this atom, when they get closer together, they start to move apart. But you also see there is some sort of pull, so that you can see the electrons here, right? Start to get attracted to the other side, right? And at a certain distance, those orbitals will start to overlap, and that creates a bond. And you can see the probability density of the electrons has now been shared, and they're evenly spaced between the two atoms. As the distance between the nuclei decrease, the probability of finding either electron of the hydrogens on either nucleus increases. Basically what that means is you can see that the orbitals are shared between the two atoms. And so instead of having one sphere, you have an elongated oval. There's a lot of attraction and repelling that's going on. So if you look at just the simplified model of the hydrogen, you have one proton, one electron. Again, hydrogen doesn't have a neutron. So the protons repel each other, the electrons repel each other, but then there's attraction between the electron from one atom to its nucleus, and then the atom or the electron to the other nucleus, and so forth. So we can see that energetically, the lower the energy, the more stable the species. As the distance of the atoms get separated, going further and further apart, you see that if we come this way, as you get closer and closer together, it becomes more energetically favorable. Okay, so it's starting with two atoms getting closer together. There will become a point where the atoms find a sweet spot where the electrons are attracted to the positive centers, but not repulsed away. As you try to squish the two atoms together, the energy shoots up because it's very energetically unfavorable. What that looks visually is we have two atoms way too close together. You can see that the overlap is great, and the positive centers are way too close. As they get separated, there's a nice sweet spot where the energy is minimized. But as they get torn apart, it's almost like having two individual atoms. What that looks like for Lewis structures is a bit different. So instead of having two individual Lewis symbols, we have a structure to take into account. We can still represent it with the dots. So for the nonmetals, the number of valence electrons is the same as the group number. So just like we did with ionic compounds, we can find the valence electrons. For example, a halogen only needs one bond to achieve octet. Group 6 needs 2 bonds, etc. Group 1, there's a hydrogen with 1 electron, a hydrogen with 1 electron. Hydrogen's octet is helium, so hydrogen wants to be like helium. As you get closer together, the hydrogens can share the electrons, and both hydrogen has what we say 2. So there's 2 electrons, and they're being equally shared between hydrogens. Instead of representing it as 2 dots, we draw a formal bond as a line like that. So when you see a line, it actually is 2 electrons. This is true for any species. So we see with fluorine, the valence electrons is 7. So there's 7 electrons around this fluorine, 7 around here. They're 1 away from filling an octet. So you can see that when they get closer together, they can share this electron. Species overlap, and the formal Lewis structure will be 2, 4, 6 electrons around here, sharing 2, so that has 8. 2, 4, 6, again, this counts as double, so that is 2 here. So 2, 4, 6, 8, 2, 4, 6, 8. The electrons that are not in a covalent bond, so this would be a covalent bond here, these guys will be called lone pairs. They are not formally bonding, but they will affect the geometry and behavior and electronegativity of a system, which we'll talk about a little bit more in Chapter 9. This structure and these valence electrons in the bond is true for all the rest of the halogens because they all have a valence electron of 7. So for chlorine, instead of a F here, you could put 2 chlorines. We can describe how many electrons will be shared through bond order. So many nonmetals can form more than 1 covalent bond. So hydrogen wants to bond once, halogens want to bond once. But carbon, if you remember, has 4 valence electrons. That means it has 4 vacancies that can have another electron stuck in there. So we say that carbon can bond 4 times. Nitrogen has 5 electrons. It is 3 away from the octet, so it has 3 locations for another electron. Therefore, it can bond 3 times. Oxygen has 6 valence electrons. It is 2 away from the octet, so it can bond twice. Now, this could be 4 single bonds, so in the case of carbon. If we just want to what we call protonate, so put some hydrogens around the carbon. Each hydrogen has 1 electron to give. That means in order for carbon to be fulfilled, it needs 4 different bonds. Hydrogen can only give 1, so you need 4 hydrogens around, so that way oxygen is complete and hydrogen is complete. Same with nitrogen. It has a complete lone pair here, but there are vacancies here, here, and here, which 3 hydrogens can go into. So you'll see that there are 3 hydrogen bonds. The lone pair still isn't bonded, so it has to be accounted for. Oxygen has 2 vacancies, 2 open spots, meaning it can bond to 2 different hydrogens, as shown. It still has the 2 lone pairs that you have to account for. It does not have to be a single bond. So oxygen has 2 holes and 2 free electrons. Carbon has 4 spaces. So instead of having 4 different hydrogens around it, you can put 2 oxygens. So that way you have your oxygens being shared, or the electrons around the oxygen being shared here and here, forming a double bond. We will pick this up in the next video.